we deal everything with geometric series and sequences. We've already discussed geometric sequence and what it entails, like the common ratio versus the arithmetic sequences we deal with, the common difference, right? And now we're going to do geometric, finite, and infinite geometric series. Remember the difference between series and sequence? Series, we're always adding the terms. So like a summation entails like the descent notation or the summation notation. The series, we're taking the values which are a geometric sequence and we're adding them all up and seeing what it actually reaches. Okay? Alright, let's go on. The sum of a finite geometric sequence. Now, a couple of things. So we have a geometric sequence here. Now, it becomes a series if I actually add these, right? I'm going to add all of these guys, and it becomes a geometric series. Okay? Now, one more thing. Today, I'm only going to show you the actual theorems or the formulas. However, there is a proof of this in your Schoology folder. Please refer to the paper written proof. I wrote it out for you, so make sure you listen to it. I know you're curious, okay? Alright, now I'm going to give you guys the geometric. The first one we're going to discuss is actually the finite geometric sequence, okay? Now, the finite geometric sequence looks like this, S sub n, because it has an ending, right? It has n number of terms. Number of terms again, okay? N number of terms, and we have a summation, right? We want the sum of 1 to n of a geometric sequence. This is an I, okay? And this is also an I. Alright? And the formula goes like this. If we take, but we have to remember also that our common ratio is not equal to 1. Okay, obviously it's supposed to be 0, right? When we multiply it per term. So we have a geometric sequence. This is the explicit formula. Don't forget, again, explicit come in handy, huh? And it's the one you like, okay? Now, explicit formula, this all sums up to this nice little sum here. You take the a sub 1, but again, I'm going to specify something here. A sub 1 means first term. It does not mean A1. It means the first term in this. Because maybe this guy, I'm going to throw you off and start this at 5. You can start at 5 based on what the formula is. Okay, it's the first term of this communication, okay? First term, and this is your common ratio here, 1 minus common ratio to the nth power, which means the number of terms, okay? Once again, number of terms. 1 minus the common ratio. So everything sums up just nicely to this. As long as your absolute value of the common ratio is not equal to 0. This is again for a finite geometric series. Okay, finite. Now what about if we have infinite geometric series? I want you to think about why there is no such thing for a common difference or an arithmetic sequence, why there is no such thing as an infinite arithmetic series. I want you to think about that. Okay, now let's go on to if your common ratio, only if your common ratio is less than 1. Only if your common ratio is less than 1. The infinite geometric series, for example, we have this guy, a geometric series, as you can see, but the common ratio is less than 1, not equal to 0, and less than 1 though, the absolute value of. That means it's fractions like this versus like that, right? This one gets larger forever. This one gets smaller if you keep on having them. We're going to do an activity within the class. A sub 1 plus, this is a geometric sequence or a series, I'm sorry. So it keeps on going forever. What is that going to converge to? Okay? So we're going to actually show you the formula. So again, S sub infinity. Sum of infinity is, so you can go from I equals 0 here, but again, I can adjust that later to something else. 1 if I want to, 2 if I want to. So we're going to do I equals 0, you have A1 or 2I, okay? And it goes to infinity, it converges to just this. So you can see how this formula is related to each other, okay? I'll explain that later too, okay? A sub 1 over 1 minus the common ratio. Now, I'm going to write a few things here, okay? Now, I'm going to write a few things. I'm going to do a short little explanation here for you, okay? Now, S sub infinity is equal, well, let's actually discuss A sub n first. You know the a sub n, right? Isn't it this? A sub 1 minus r to the n over r to the n over 1 minus r. So see, if you have an infinite finite geometric series, it's going to convert to this one value. This is just one number, okay? But I want you to think about something. What if my common ratio is actually, let's say, so you guys, the n is infinity. The number of terms is infinite number of terms, okay? Common ratio is less than 1. That means I have like a half. I have a 1/4. I have 5 8. These fractions are less than 1. What happens if you keep on having a half, half of a half, half of a half, half of a half, half of a half, or 1/4 of a 1/4, 1/4 of a 1/4? I take a quarter of a dollar, quarter of a quarter, quarter of a quarter of a quarter. You know, it gets smaller and smaller, right? These values, as it reaches infinity, as it goes to infinity, like your n goes to infinity, that means the number of terms as it goes to infinity, these get smaller. How small? How small does it get? Very small. Smaller, smaller. What does it reach to? You guys, you have a common ratio, any of these values here that are less than 1, it goes to infinity, right? What does it reach? You're right, it's so small that it almost becomes 0. Think about it. Half of a half, half of a half, half of a half, it goes to 0. That means this formula was literally derived from this guy here, the finite geometric series. Because the r is less than 1, sorry, less than, well, the absolute value that is less than 1, therefore, this actually eventually goes to 0. So what happens to that? This becomes infinite is equal to a sub 1 over 1 minus r. Because this becomes a sub 1 minus r, 0, right? 1 minus r to the 1 minus r. Because r to the n equals 0. So I'm going to explain the formal proof for you guys. You can look at that on school so there's a full page on my proof. And this side, it can be simply rewritten in quantity. Okay? So, summation of an infinite geometric series, it just goes to this value. Okay? Alright, let's do some examples now so you can get a better idea. Alright, so let's go into, let's do example number 60 from your book, okay? Read number 60. So make sure you stop the video if you have any trouble. We're going to do 60 and 78, but we're going to do 60 first, okay? Now look at 60. Alright? Again, let's actually decide. Is this a finite or is this an infinite? And clearly, this formula kind of tells you that this is a geometric series, right? Okay? Alright. But wait, you might be complaining that this formula you don't recognize it. Because the geometric sequence that you guys learned the formula for is a sub n, a1, r to the n minus 1. Well, I'm going to show you how this is related to that in a step, okay? Alright, so you know that if you want to find the sum of a finite geometric series, the formula you have to use is s sub n, right? S sub n is equal to a sub 1 minus r to the n over 1 minus r. So this is about everything that you need, okay? So what is n? What is their number of terms? 50, 0. 0 to 15 is about 50 minus 0 is 15, so we have to add 1 to the inclusive, right? So it's 16 number of terms. Keep doing that, right? Don't get confused here. Now, we also need a sub 1. So I'm going to put quotes around a sub 1. Why? A sub 1 indicates the first term of this, okay? What's the first term? You have to plug in a 0. So we're plugging a 0 here. When you plug in a 0 here, to get 4 to the third, 0, which means it's 1 times 2, which is 2. See, make sure you understand that. I'm going to start a calculation here, okay? So 2, 4 over 3 to the 0th power, which ends up being 2. So your a sub 1 is 2. What's your common ratio? Because another thing that we use, right? The common ratio is usually 1/3. Okay. So now let's try it. S sub 16, because there's 16 number of terms, is going to equal a sub 1, which is 2, 1 minus 4/3, right? To the 16th power, only that's 4/3 though, over 1 minus 4/3. Okay? Alright, so that actually becomes, of course, we did a calculator for this, 592.647. Okay? 592.247. Now, I want to point something out here, okay? I'm going to do something else. Here, today, I know that a lot of you guys are thinking, well, I don't really recognize this formula here. So you're used to this formula here. Remember I talked about that briefly at the beginning, that you recognize this. So how can we rewrite this formula using this formula here? Just ignore that part for now, guys. I'm going to ignore it for you. Just don't look at that, okay? So, you know how right now it's written as n equals 0, 15, 2, 4 thirds to the nth power? But I know that you don't recognize this formula completely, so how can we rewrite this, right? So think about it. How about if I rewrite this as n equals 1? Think about what was shown here, and I would show up as a sub 1 is 2, and my common ratio doesn't change. So what would change here then? I need this to produce what value? 2 when I first start this. So you're right. This is just 1 minus 1 here, right? And if I plug in a 1 here, it's 1 minus 1, which is 0, which is 2. So what would go here then? 16. Just plug it in now. 16 would be the last number. Okay? So you see how it's adjusted from here to here, the summation notation? But in the end, here, do the same thing. A sub 1, the first term of this sequence is also going to be 2. The common ratio is 4 thirds, and it goes to n equals 16 terms. It's going to give you the same value as this. Okay? Alright, this time the next one, which is this infinite geometric series. Okay? Well, how do you know that it's infinite, you're asking? Well, it's pretty obvious. I'll show you why. Find the sum is going to tell you. Okay? It's going to tell you to find the sum. And you have to be able to recognize that this is a geometric series. Okay? Now, here, you know for sure it's geometric, right? And you know it's infinite. How? Because it says to go infinity in the end. Okay? You know you're going to be using this formula right here. The geometric infinite series. You're going to use this formula, a sub 1, 1 minus r, right? Or, you can just think of it as a sub 1 over 1 minus r. Okay? So let's calculate for a sub 1. What's your first term? Notice I say first term, not a sub 1. Your first term is when you plug in a 0 to this geometric sequence. When you plug in a 0 here, you get 1. So 0.2 to the 0 power is 1, you get 4. What's your common ratio? It's 0.2, or you can write this as 1/6, however you like, okay? Now, that's all we need, right? So ready. So S, the geometric series of this infinite series is going to be your a sub 1, which is 4. 1 minus your common ratio, 1/6. So you get 4 over 0.8 or 4/5, which is the proof. We're going to do a nice proof of this in class. I'm going to take you together, okay? So don't worry if you don't totally see how this works. It's okay if you understand the formula just for now, okay? Also, if you're curious, look at my proof, okay? Number 68 is here. It says use summation notation to express the sum. Ooh, this one's a little bit lengthy, okay? Use summation notation to express this sum. What does that mean, right? First, let's actually discuss what kind of sum, what kind of sequence, is this a sequence or is this a series? This is a series. You're adding or subtracting the values, right? Right, this is a series. What kind of series is it? What kind of series? So we have to look at all the values, right? What's the relation between 15, negative 3, 3, 6, all the way until negative 6.5? You gotta see, right? You gotta see if there's a common difference or a common ratio. So what is it? Pretty clear that we have a geometric sequence, right? Geometric. Because you have a common ratio. Do the division. Negative 3 divided by 16. 3/5 divided by negative 3. This is from the following previous lesson, right? It's going to be negative 1/4. Or we can write it as negative 0.6. Right? Right? That's the first step in finding this. This one has a lot to do, so make sure you slow down. Second step, you have to calculate for a sub n, right? So what's the geometric formula? Geometric sequence formula. Well, do we know everything yet? And this is, again, an explicit formula, okay? Do we know everything, guys? Let's check, okay? A sub n is equal to, what's your a sub 1? 16. What's your common ratio? Oh, negative 1/6. And what's n minus 1? Here's your explicit formula. Okay. Okay, now we might be ready to start, right? So they just use summation notation to express the sum. We need to find the sum of them. Okay, so we're going to be like, okay, but wait, this is a finite, obviously, because it ends here. So we don't really know our n. We don't know that. I mean, we know our a sub 1. We know we're going to have to use this formula, right? We know r, the common ratio, and we know a sub 1, but we don't know the n. So we need to figure that out. We have to look at this value here. So like, how many times did I apply the common ratio in order for us to get negative 3 over 625? What is that, right? We got to calculate that. And that might require a little bit of algebra, so hang on there with me, okay? Alright, so you guys, we know that negative 3 over 625 equals, right, a sub 1, which is what? A sub 1, what? A sub 1 is 15. And your common ratio is negative 1/6 to the n minus 1 power. So we have to do the calculation. I'm going to first divide by 15 to both sides, and I end up with this nice value. Negative 1 over 3125 is equal to negative 1/5 n minus 1. So we need to calculate the exponent, right? So obviously we can use log, remember guys? You can use log, or you can use common base. So there's some, there's a 3125 here. So we can kind of give you a hint that you can probably make this into a same base of 5. Let's do that, okay? So I'm going to go negative 125. Instead of writing it as negative 3125, is there any way I could write that in terms of negative 1/6 to have the same base of that? And you're right, it's actually 5. Negative 5, or 5 to the 5th power is 3125. So I write that as the same base as this. So now I know the exponent has to be equal in order for this equation to be equal. 5 equals n minus 1, and let's see if this. Wow! We've now calculated that a sub 6 is actually negative 3625, which was the term that they gave us. This guy is a sub 6. We can conclude that now. Now we know everything we need to know. So I'm going to slide this over. Now let's finish calculating. It's going to be a sub 6, right? A sub 6. A sub 6 is equal to a sub 1, which is 15. 1 minus our common ratio is negative 1/5. Notice it's still minus a negative 1/5 our common ratio. Okay? N, which is 6, is 6 number of terms, and 1 minus a negative 1/5. Again, you guys notice, if your common ratio is a negative value, you have to indicate that as a common ratio. Don't try to change the signs, okay? That's bad calculation or bad math, okay? So if we actually wrote this into summation notation, it would look like this, right? It would be n equals 1 all the way to 6, right? So 6 minus 1 is 5, so that's 6 total terms. 15 are explicit formula here, n minus 1. Or, I know a lot of you guys are like, I don't like this notation. You can do n equals 0 if you wanted to, right? And you can go up to 5. It's going to be 15, negative 1/5, and n power. But if you don't understand this, please stop by really quick and I can explain that to you very simply. Now, if I calculate this, I actually end up with this. 7812 over 625. Of course, it's the top step, so you need a calculator. Alright, now try some, take a Schoology for some homework problems you can practice, okay? It's a little confusing for now, but you can do it! Bye!